Me, I'm Mason. That's Carson over there. This is our statics problem. We're doing problem 16. I've already wrote it on the board here. Now, first thing you want to do with a statics problem is draw your free body diagram. And first, I've drawn it, obviously, but the forces that I've gotten from this 1200 Newton force and this 600 Newton force comes from these two. So we want to treat this distributed load as a rectangle down here and then a triangle up here. So we solve this triangle using the 1/2 base times height. And of course your height is going to be 200 because remember you're subtracting this 200. So you're getting 600 newtons and you get your distance because it's 1/3 from the tallest end over this way. Now for this, it's the rectangle, it's just uniform right down the middle, just base times height. So that's going to end up being 1200 newtons. Now, of course we drew our A of X and our A of Y and then our B of Y over here. Now we only draw B of Y because the B is a roller, so there's no force in the X direction. All right, next what we're gonna do is we're gonna do our sum of moments.
Wait, Mason, wait.
Yeah.
You didn't put the X-axis and the Y-axis. You didn't label them, all right?
Oh.
Here, let's play around, all right? Show you how I'm right.
Shoot. He just sucks, I guess. But like I said, or like he corrected me, every time we have a statics problem, we need to label our X and our Y direction. Now next what we're gonna do is our sum of moments at point A. Now this is gonna be negative 1200 times 3, then negative 600 times 4, plus 6by. Now once you solve for by, you should end up getting 1,000 kilogram meters.
Well, Mason. Not kilogram meters? It's newtons, all right? Let's play around with it.
This bum over here.
This is kilogram meter.
I guess it is newtons after all.
Yep.
Yeah. All right. So after that, we want to do our sum of forces in the X direction. And look, we only have one force in the X direction, which is A of X, which is just going to equal 0. And then sum of forces in the Y direction, we have AY, BY, and then minus 1200, and then minus 600. Now, we already have BY because of our equation up here. So once you calculate AY, you're going to end up getting negative 800. Newtons, of course. But after that, it asks for the shear, the bending moment, and the normal force at point C. So what we want to do, we just want to break point C. But we can do that over here on our free body diagram. So we want to break point C. So we're going to take the left side of point C because there's a force in the X direction, and we're going to redraw that over here. Now, since we only have half, we're taking our distributed load as only having the magnitude of half of this. So it's not going to be 1200 or 600. So what we're going to do is we're going to have 600 right down the middle, and then we're going to have 150 over here, and 600 is going to be at a distance of 1.5 feet, and then
No, Mason, it's meters, not
meters.
feet.
Oh,
Meters. Oh, I'll prove you're right. Paint on it really quick.
that out of here. All right.
Give me that back.
Of course, yeah, it is meters instead of feet. And of course, we're gonna have 1.5 meters to 600, and then we're gonna have 2 meters to 150. Now, there's also gonna be our A of X and A of Y over here. Now, there's also gonna be our shear force. Then you have your bending moment, and then your normal force. Now, the easiest one to find is the normal force, because what you want to do, you just want to do the sum of moments in the x direction, and that's just going to get you a of x plus n, and of course that equals 0. A of x already equals 0, so that just means n equals 0. Next, what we want to do is you want to sum our forces in the y direction, and that's going to be ay minus 600 minus 150 minus vc, which is our bending moment. Now, once you calculate all that out, you're going to get, or not our bending moment, our shear force, sorry, and once you calculate all that out, you're going to get 50 kilogram meters. So next what we want to do...
I told you, it's not kilogram meters.
My bad.
It's newtons. Newtons, get that in your head. All right, again.
Yeah, I mean, this guy sucks. But looking back at it, yeah, it's newtons, and it's a mistake I make all the time. But one other mistake I just realized that this bum didn't call me out on. I forgot to label my axes, so y direction and x direction. Now, most time, TAs will take off points for that because that's what they're told to do, which sucks, but it is what it is. So finally, to get our moment, or our bending moment, it's going to be sum of moments at C, I guess. And it's going to be your bending moment minus AY times 3 plus 600 times 1.5 plus 150 times 1. And once you solve all that out, your final answer for your bending moment is going to be 1350 meter newtons.
Mason, nobody uses meter newtons. It's always Newton meters, all right? I'll prove you right.
He wants to lose again, we'll see. Now, normally, I mean, meter newtons works, but normally everybody just uses Newton meters, and in the field, you always want to make sure everybody has the same orientation of the symbols in that. So, of course, Newton meters. And those are our answers, and the problem is solved. Thank you.
Good work, Mason, good work.